Hello, and welcome to this video. So in this video, we're going to talk about OSPF basics. OSPF stands for Open Shortest Path Fast. It's one of the dynamic routing protocols that are used at the enterprise. It's one of the most widely used dynamic routing protocols in enterprise. So we have discussed about static routes already, and we have seen that static routes are manually configured. Now what this means is that the network administrator, yourself or me, will log into the devices like routers and configure static routes manually. Tell the router that if you want to go to network N, you should send the packet to the next hop NH, and so on and so forth. Sometimes you have several networks as the destinations. You have network N, network Y, network Z, network W, and so on. For each of the destinations, a network administrator needs to configure a separate static route for it. And what's more, if the network topology changes for any reason, either by error or administrative adjustment, static routes would have to be manually adjusted. Now that restricts the large-scale application of static routes on live networks. This is exactly the reason why we have dynamic routing protocols, and they are widely used on live networks because of their high flexibility, high reliability, and easy scalability. OSPF, the Open Shortest Path Fast, is a protocol that is widely used in the enterprise network today, and it's one of the dynamic routing protocols. Precisely, it's the dynamic routing protocol, one of those that uses the link state routing algorithm. So this chapter introduces the basic concepts, the working mechanism, and basic configurations of OSPF. So upon completion of this chapter, you'll be able to describe the advantages and to describe the classification of dynamic routing protocols in general, and then you'll be able to describe the basic OSPF concepts and the typical usage scenarios of OSPF, the working mechanisms of OSPF, and you'll be able to implement the basic OSPF configuration. In order to achieve these objectives, I'm going to break down this chapter into three subsections. First of all, we'll talk about the OSPF overview. After the OSPF overview, we'll discuss the OSPF working mechanism. Once we're done with the working mechanism and the overview, we'll have understood enough OSPF to be able to tackle some OSPF basic configuration. So in item number 3, we'll fire up a network topology and configure OSPF in the topology and see how OSPF lands routes and understand the OSPF routing table. So before going any further, let us look at the overview of OSPF. In fact, before looking at particularly the overview of OSPF, why should we even think about dynamic routing protocols? Again, static routes are manually configured and they are manually maintained. And the command lines for static routes are very simple and they are very clear. Static routes typically apply to small-scale networks or very stable networks. You won't need to change anything in the network. You need to set it up once and it almost never needs any modification whatsoever, which is not true for most networks. Now, these static routes with those characteristics have a number of problems, have a number of disadvantages. First of all, they are unable to adapt to large-scale networks. If the devices increase, the configuration workload is going to increase sharply. Secondly, they are unable to dynamically respond to network changes. If something changes about your network topology, the network cannot automatically convert. It cannot automatically learn the new topology and work as expected. The static routes must be manually modified for every change that happens to the network. For example, we have a network with R1 and R2 and R3 interconnected in a ring format. And we have a route from some network on R1 leading to some network attached to R2. Currently, the static route has been configured directly like that. So what happens if this link right here between R1 and R2 gets a problem? We need traffic to be passing this direction to reach R2 because traffic can as well pass that side. Well, the problem with static routes is that the router will not change to this path itself. You'll need to manually configure the static route to tell R1 that, we've gotten a problem with this link. If you need to go to the network on R2 now, please send your packets through R3 in order to reach R2. That is the general problem with static routes. And it is the main reason as to why we need dynamic routes. Static routes also have their benefits. For example, R1 and R2 do not need to exchange any protocol packets in order for them to work with static routes because you told them manually as the administrator that if you have packets headed to network M, please send them onto R2 at that point. we don't need to exchange any protocol packets. For all dynamic routing protocols like OSPF, like ISIS, like BGP, like AirGP, we shall need the protocol to exchange some packets to establish the neighbors, to know that this neighbor is so and so, to know that this IP address is in this place. There are some packets that are going to be exchanged in our network. Well, that is overhead, and sometimes it becomes too much and slows down our network, makes our network quite busy. But why do we have to go for dynamic routing protocols? Because static routes have these major problems. So what are dynamic routing protocols? How many are they? How are they classified? We are going to start looking at information like that about dynamic routing protocols. Again, because of the problems of static routes is the reason why we need to use dynamic routing protocols. But before we dive into dynamic routing protocols much further, let us try to classify them. Well, when we classify dynamic routing protocols, we can classify them in two main ways. First of all, we can classify them based on coverage by autonomous system. Point of application, where are we using the dynamic routing protocol? Are we using it within the autonomous system, or are we using it outside the autonomous system? Well, an autonomous system is a single network under one administrative control at the basic. So, are we using the dynamic routing protocol within an autonomous system, or are we using it outside the autonomous system, like to connect different autonomous systems together? So if we are using the routing protocol within an autonomous system, such routing protocols are called IGPs, Interior Gateway Protocols. In this example, we have three of them listed: RIP, Routing Information Protocols, OSPF, Open Shortest Path Fast, and finally ISIS, Intermediate Systems to Intermediate Systems. Now, there are also protocols that are used outside the autonomous system. They are used to connect different autonomous systems together. And in this case, they are called the Exterior Gateway Protocols, the EGPs. The main EGP we discussed today is BGP, Border Gateway Protocol. That's just one way of classifying dynamic routing protocols by autonomous system, in which we have two types, IGPs and EGPs. Now, the other way of classifying dynamic routing protocols is by their working mechanism and algorithm. Which algorithm do they employ when they are making calculations? Which algorithm do they base on to make their calculations, to determine their routes? Well, when we classify routing protocols, dynamic routing protocols in this mode, there are two or three types of dynamic routing protocols. First of all, we have the distance vector routing protocols. And in this example, mainly is RIP. Secondly, we have what we call link state routing protocols. The distance vector routing protocols use what we call distance vector algorithm. The link state routing protocols use what we call the link state algorithm, really. And we have two examples in this type: Open Shortest Path Fast, OSPF, and ISIS, Intermediate Systems to Intermediate Systems. Well, we don't see BGP in this classification because apparently BGP has a different algorithm it uses that we call the path vector algorithm. The path vector algorithm. Now, the path vector algorithm is a modification of the distance vector algorithm. So BGP is not exactly using the distance vector algorithm, and it's not even link state because it uses the path vector algorithm, and that makes it three, if you would say so. So distance vector routing protocols, link state routing protocols are the two main ones we have if we classify by working mechanism. But what are distance vector routing protocols? How do they work? Why do we call them distance vector routing protocols? What are their differences from link state routing protocols? Would we rather use distance vector routing protocols or link state routing protocols? Well, if a router is running a distance vector routing protocol, it's going to periodically flood routes. Periodically, it sends its own routing table to the neighboring router. It says, these are the networks I know of. Please add them to your own table. If you have any traffic headed to any of those networks, just send it to me. Now, through this kind of route exchange, each router learns routes from the neighboring routers and installs those routes in its own routing table. What does that mean? It means that each router on the network is clear only about where the destination is and how far the destination is. That's important. Where is this destination? Well, it's on the other end of router 3. How far is it? It is 2 routers away from me. Those are the two things a router will be aware of when it's running a distance vector routing protocol. The problem is the router is unclear about the entire network topology. It can't calculate by its own the distances. How far is this network? Would I rather pass here or would I rather pass here? If we have another path to R3 like that, this router can't calculate independently which of these two paths is the best to reach 3.3.3.3. it's going to get information from R2 and then information from R3. It's called routing by rumor, and based on that information, it will choose. It doesn't know the entire scale of the topology. It doesn't know the entire topology on its own. It doesn't do its own calculations. It takes calculations that others have sent it. Now, there's an important aspect I want to draw here. The first item that happens is it receives routing updates. It receives the routing information from another router. In this case, router 1 receives routing information from router 2. After receiving it, it calculates its own entries for that routing information. For example, router 2 says, network 3.3.3.3 is one router away from me, is one hop from me. So router 1 says, so if I'm getting it through you and it's already one hop away from you, it means it's 2 hops away from me. Well, that's what it knows. It does that calculation, and after making that calculation, let us just say, for purposes of explanation, there was another router here, router 4. It sends it this side after send update. So after calculation, it sends the update. Well, you realize this system has a little bit of a problem. It makes the entire process a bit slow, and it makes it a rumor. So router 4 has to calculate based on what router 1 calculated, and router 1 has to calculate based on what router 2 calculated, and router 2 has to calculate based on what router 3 calculated. So if router 3 reported an error, if, for example, this network disappeared and router 3 has not told this guy the network disappeared, he will continue assuming the network is there. Routers receive updates, they make their own calculation of the routes, and then they send updates. This system is a bit slow. A more efficient system, in fact, the system used by link state, the routing protocols, is receive, send, then calculate. Well, this enables all the routers to calculate almost at the same time. And we're going to talk about this when we talk about link state routing protocols. Well, this is what distance vector routing protocols work as, and it's called routing by rumor. So what about link state routing protocols? Well, I've already mentioned, and I wish to remind you that we say distance vector routing protocols use the concept of flooding routes. They flood the actual already calculated routes. Well, routers running link state routing protocols do not flood routes. They flood link state adverts, the raw material of routes. So different from a distance vector routing protocol, a link state routing protocol advertises link state information rather than routes in the routing table. Routers that run a link state routing protocol establish a neighbor relationship first and then exchange link state adverts. So first of all, router 1 needs to establish a relationship with router 2 and router 4. Router 4 establishes a relationship with router 1 and router 3. Router 3 establishes a relationship with router 4 and router 2. Router 2 establishes a relationship with router 1 and router 3. Once all the relationships are established, router 1 is going to send its link state adverts to router 2 and send its link state adverts to router 4. Every router will do the same. Now, each router shares with its neighboring routers its own link state adverts. And what are link state adverts? It's showing the status of these links. So router 1 is like, I have this link on me, it's up, and this is its IP, this is subnet mask, and this is the neighbor on the other end of the link. I also have this link on me, it's up, this is its IP address, and this is subnet mask, and it has this neighbor on the other end of the link. Well, router 2 does exactly the same thing, shares its link information out of that interface and out of that interface. Router 3 does the same thing, shares its own link information out of that interface and out of that interface. Router 4 does exactly the same thing, shares its link information, link status information out of all those interfaces. Once each router has finished sharing the link status information, like the cost of the interface, the connected interface name, the connected interface bandwidth, the subnet mask of the interface, and so on and so forth, each router in the topology, in this case router 1, 2, 3, and 4, will all have the same link state database created. A link state database is the table inside the router in which we record the link state adverts. So all routers have finished exchanging their own link state adverts, and they have stored link state adverts they have received into their link state database, LSTD. All the routers now have the same link state database. Each router generates link state advertisements and adds the received link state advertisements to its own link state database. So routers learn the whole network topology, as opposed to distance vector routing protocols. So the router stores linked state adverts in linked state database. The linked state database contains the description of all router interfaces on the network. The linked state database contains the description of the entire topology. Because now look at router 1. He knows the status of his own links. He has received the status of that and that from router 2. He has received the status of this and this from router 4. He has received the status of this and this from router 3. And what has he received about them? He has received the link bandwidth, he has received the cost, he has received whether it's up or down, he has received the neighbor on the other end. So he can actually know that router 4 is connected to router 3. Because router 3 told him that on this link, my neighbor at the other end is 4.4.4.4. And router 4 told router 1 that, oh, on this link, my neighbor at the other end is 3.3.3.3. So router 1 is able to calculate the entire topology by his own. And what does he use to calculate the topology? He uses Dijkstra's algorithm, or the shortest path first algorithm, to calculate the topology. Well, what he actually calculates is called the shortest path tree, the SPT. So we use the shortest path first algorithm to calculate the shortest path tree. And now, from the perspective, for example, of router 3, router 3 is aware that I can reach router 1 from here. I can reach router 2. In this case, you can see router 3 can reach router 1 through this link. Router 3 can reach router 2 directly. In fact, you will prefer this link, as you can see. So all this is going to be calculated by each router. Each router will have something like that called the shortest path tree, which is a loop-free tree, and it is itself the root of that tree. So this is what is going to happen. Once we are finished calculating the shortest path tree, we shall get the entries. Each router will get the entries from its own shortest path tree and enter them into its routing table to generate the routing entries. Ultimately, the router installs the routes for the calculated preferred paths into its routing table. Now, each router has its own routing table. Let us look at this kindly again. First stage is flooding linked state adverts. But in fact, let's call it the second stage, because in the very first stage, we are supposed to establish neighbor relationships. So first, we establish neighbor relationships, and after establishing neighbor relationships, we flood the linked state advertisements. After flooding the linked state advertisements, we go ahead and use the linked state advertisement to populate our linked state database. Once all the linked state databases are the same, then we go ahead and use the Dijkstra's algorithm, shortest path first algorithm, to calculate the shortest path tree. Each router does this independently, and once each router has its own shortest path tree entries, it's going to get all of those entries and use them to generate the routing table. Based on the shortest path first calculation results, each router installs routes into the local routing information base. 4 stages, 4 steps that any linked state routing protocol will use to generate the routing table. And what are those stages? Once again, in summary, stage number 1 is setting up neighbor relationships. How the hell do these routers set up neighbor relationships? How does router 1 know there is router 2 over there? How does router 3 know there is router 1 and router 3 over there? Well, we're going to look at that. Once the neighbor relationships are fully set up, we start exchanging link status information into, and we all put the link status information we receive and our own into the link state database. Once we all have the exact same link state database, identical link state database, we each independently do path computation using the shortest path first algorithm to generate the shortest path tree. Once each one has his own shortest path tree, we are going to get hold of the entries in the shortest path tree, the best paths to each and every other node in the topology, and use them to generate the routing information base or the routing table. Well, those are the 4 stages that all link state routing protocols use. All routers running link state routing protocols use, whether they're running OSPF, whether they're running ISIS. Well, in this course, we shall talk about the case of OSPF, but ISIS works exactly the same way. So, what the hell is this OSPF? Well, let us try to bring this down to OSPF. So, as I've mentioned, OSPF is a typical link state routing protocol, and it's one of the most widely used IGPs in the industry, interior gateway routing protocols. There are two versions of OSPF. We have OSPF version 2 and OSPF version 3. In fact, they are both defined in different documents. OSPF version 2 is defined in RFC 2328 and OSPF version 3 is defined in RFC 2740. Why do we have both of them? Well, OSPF version 2 is specifically designed to work with IPv4. It does not know how to handle IPv6. There is different fields that are added into OSPF for it to be able to handle IPv6. So OSPF version 3 is specifically for IPv6. When you hear OSPF version 2, that's IPv4. When you hear OSPF version 3, that's IPv6. Now, for the rest of this course, unless otherwise mentioned, when you hear me say OSPF, I'm really saying OSPF version 2. OSPF routers exchange link status information like any other link state routing protocol, but not routing information, not routes. Link status information is key information for OSPF to perform topology and route calculation. An OSPF router will collect the link status information on the network and store the information in a link state database. Routers are aware of the intra-area network topology and are therefore able to calculate the loop-free paths independently. Each OSPF router uses the shortest path first algorithm to calculate the shortest path to each specific destination. Routers therefore generate routes based on these paths and install the routes in the routing table, install the optimal routes in the routing table. OSPF supports VLSM. We'll look at this concept in IP addressing, variable length subnet mask mechanism, and also supports manual route summarization. We'll introduce route summarization in IP routing basics. The multi-area design enables OSPF to support much larger networks, so it makes it way more flexible than static routing or some other dynamic routing protocols. So where in our typical campus network do we deploy OSPF? Well, we know that we have a typically 3-tier network, sometimes a 2-tier network. Let us talk about the 3-tier network. 3 layers, where we have the access layer, where we have the aggregation layer, and we have the core. So OSPF is typically going to be running between the core and the aggregation layer to implement reachable routes on the entire campus network. It's going to be running around here. The access layer will not be running OSPF. Well, I hope these layers do not confuse people with the OSI layers of the physical layer, of the data link layer, the network layer, and so on and so forth. These are just the tiers, the hierarchical architecture of a typical campus network. Well, that is the very basic of link state routing protocols and OSPF in particular. In the next video, I'll be talking about the basic concepts of OSPF, concepts like the router ID, concepts like the area, concepts like the cost, and a few other concepts about OSPF before we start diving into the working mechanism of OSPF. I hope this has been informative for you. Thank you for viewing.